Okay, let's dive into this. Have you ever looked at a car tire or maybe a massive heavy-duty industrial rubber belt and just wondered how engineers formulate them to be so incredibly tough? Well, the secret often comes down to an essential material called carbon black. But here's the thing, rubber engineers don't just call up their suppliers and ask for generic carbon black. No way. They use a highly specific, totally hidden language to organize and request it. So today, in this explainer, we're going to crack that carbon code by exploring the really fascinating world of the ASTM D1765 standard.
Here's a quick roadmap for this explainer. Section 1, Cracking the Carbon Code. Section 2, Character 1, Cure Rate. Section 3, Character 2, Surface Area. Section 4, Measuring Carbon Black Properties. And finally, Section 5, Registering a New Grade.
Section 1, Cracking the Carbon Code.
So, when rubber engineers are talking shop, they'll casually throw around designations like N110 or S315. Now, to the untrained eye, those just look like completely random serial numbers, right? But they aren't. They are actually information-dense codes detailing exactly how a specific rubber compound is going to behave once it's mixed and cured. If we take a look at the official standard, which is governed by ASTM International, we see this mandated 4-character nomenclature system. This document is, literally, the dictionary that keeps the entire global rubber industry speaking the exact same structural language.
Let's move to and see how this builds, because the code always follows a rule of progressive disclosure. Step 1 is always a single letter. Step 2 is always a single digit. And then Step 3 relies on 2 final digits. Each little piece of this 4-character puzzle unlocks a totally different set of physical properties about the material. It's kind of like a secret handshake for chemistry.
Section 2, Character 1, Cure Rate.
Let's decode that very first character. So the crucial point is understanding the difference between the letters N and S. If the code starts with an N, it indicates a normal curing rate. These are your typical furnace blacks, and they haven't received any special modification to alter how they influence the rubber's curing process. On the other side of that spectrum, we have S, which stands for a slow cure rate. These are traditionally channel blacks, or furnace blacks that have actually been chemically modified specifically to slow down how fast the rubber cures. Moving right along to Section 3, Character 2, Surface Area.
Now, what's really interesting about this slide is the second character. It's always a single digit, and it acts as a proxy for the average nitrogen surface area of the material, revealing a really fascinating inverse relationship. The standard essentially divides surface area into 10 arbitrary groups, numbered 0 through 9. A lower digit, like group 0, actually means a massive surface area, specifically greater than 150 square meters per gram. Imagine a highly porous, incredibly complex microscopic sponge. On the flip side of that, a higher digit like group 9 means very little surface area, just 0 to 10 square meters per gram. So that indicates a much smoother, way less porous particle.
Okay, so we've cracked the first 2. Highly descriptive characters. But what about the final 2 numbers? Well, unlike the highly specific letter and that surface area digit, the 3rd and 4th characters are actually just arbitrarily assigned digits. They don't represent a specific physical measurement or some complex formula. They're simply assigned to round out the code and give that particular grade a unique, permanent identifier.
Section 4, Measuring Carbon Black Properties. Now that we've got a handle on the naming convention, let's get into the hard physical science and the standardized tests that actually back up these classifications. Looking at this dense data matrix pulled straight from the standard, and I know it looks completely overwhelming at first glance, it perfectly illustrates the sheer volume of consensus data that ASTM actually governs. Every single active grade of rubber carbon black, from N110 all the way down to N991, has a designated specific place in this table, mapped to highly specific target and typical physical values.
Let's distill that overwhelming table down to the essential tests that actually matter for quality control. The standard strictly mandates testing for iodine absorption number and oil absorption number, or OAN for short. These help establish what the standard calls target values, which are the exact specifications that producers center their entire manufacturing processes around. Then, there are typical values established for things like tint strength and pore density. And they don't mess around with impurities either. Sieve residue absolutely cannot exceed 1,000 parts per million of 45 microns, and the amount of fines in a bulk shipment, that's capped at a strict maximum of 7% for most grades.
And finally, Section 5, Registering a New Grade.
So getting a brand new type of carbon black officially recognized in that massive table, not easy. It's a really strict gatekeeping process governed behind the scenes by ASTM Subcommittee D2441. Step 1 is submitting all the technical data directly to the subcommittee chairman. For Step 2, they must confirm the material is actually commercially available. No theoretical, lab-only concepts allowed here. Step 3 is assigning the actual characters, deciding on the N or S, calculating that surface area digit, and arbitrarily assigning those final numbers. And finally, Step 4 is a mandatory one-year review period, where those newly added values can be fine-tuned based on pooled production data over time. Oh, and a quick side note, you absolutely cannot use an inactive N or S designation until it's officially reactivated by the subcommittee.
This brilliantly illustrates how seriously the committee takes this global standard. They demand rigorous, undeniable proof. A requester can't just invent a grade out of thin air. They have to submit highly specific target values for iodine number and OAN, plus a full battery of typical values ranging from nitrogen adsorption and compressed OAN, all the way to tint strength and pore density. Basically, you have to scientifically prove the physical profile of the material before it ever earns its official 4-character code.
It's honestly fascinating when you step back and think about it. Look around. How much of this invisible standardization is holding your world together right now? Every single time you drive a car, fly in an airplane, or rely on any kind of industrial machinery, the secret language of ASTM D1765 is silently working in the background. It's the invisible safety net, ensuring the precise safety, durability, and consistency of every engineered rubber product you interact with daily. I hope this explainer sheds some light on the hidden codes all around us. Keep questioning and keep learning.